Okay, hello and welcome back. So in today's video, we're going to continue our exploration of differential equations. So we've had a video on constant coefficient second order differential equations that were homogeneous in nature. So second order differential equations, our coefficients, we can already look here, these functions were constant and it was homogeneous, meaning the right hand side was equal to 0. Then we were like, okay, what if the coefficients were not constant? And we looked at Cauchy-Euler differential equations. Today, we're going to be taking a look at non-homogeneous differential equations, meaning differential equations of this form, y double prime plus p of xy prime plus q of xy, which we should be feeling comfortable with. But now the right-hand side is g of x, some sort of function of the variable in question. So thus far, it's just been homogeneous. That being said, if you've not seen the constant coefficient differential equation or the Cauchy-Euler differential equation video, I highly encourage watching that. Perhaps the constant coefficient is of most use, so for now I'll just be assuming that we're comfortable with that material. But today we're going to be looking at when the right-hand side is not 0. So the general procedure for how we're going to solve these differential equations is first we'll solve the homogeneous version of the differential equations. So we'll take this g of x and pretend it's equal to 0 and solve that differential equation. That will give us a solution, which we will call the complementary solution, denoted y sub c. From there, we are going to find a single particular solution, y sub p. That's what we'll denote it. And notice how I'm underlining the word single. If we were just posed with this differential equation right here, where the right-hand side was not equal to 0, we should be thinking that, okay, there's perhaps a whole class of functions that would satisfy this differential equation. Because we saw that with homogeneous differential equations, that it was an entire class of solutions. We were taking a linear combination of two solutions, and any linear combination would suffice. So it turns out finding that class can be quite challenging. However, we can utilize our complementary solution to generate the class. But in order to generate it, we just need one particular solution, one single function that solves the differential equation. So we're just looking for one function instead of an entire class. The complementary solution handles that. And that's why our final solution will be y, which is equal to the sum of the complementary solution with the particular solution. So let's explore why our solution is y equals y sub c plus y sub p. Just make sure that it actually does work as a solution. So we have our general form of the differential equation written here. And we note that y sub c was our complementary solution. It solves the homogeneous differential equation, where the right-hand side was equal to 0. Y sub p is a solution, a single solution to our non-homogeneous differential equation. So to confirm that y equals y sub c plus y plus p is indeed a solution to our differential equation, let's just substitute it in and ensure that it gets us the right answer. So rewrite our differential equation here. Our value for y is now equal to y sub c plus y plus p. When we take the second derivative of that would be y double prime sub c of x plus y double prime p x. And then we add to that p of x times the first derivative of y plus q of x times just y in general. Just a careful thing to note, there will be differences between the subscript p and then this p of x function. Perhaps I should have chosen better variables for these two, but hopefully it's okay. We can distribute these in, and we get this entire quantity here, just dropping the parentheses, and then we'll group by like terms. So within these first brackets, we have all of the y sub c terms. And within the second bracket, we have all of the y sub p terms. But notice that this is identical to the left-hand side here, except instead of y, it's just y sub c. Well, that's equivalent to putting y sub c into this equation. And we know that y sub c is a solution, which means this evaluates to 0. So this also evaluates to 0. Similarly, when we look at the y sub p terms here, this differential equation is equivalent to this with y sub p substituted in. Since y sub p is a solution, that must be equal to g of x. So the second bracket equals g of x. So the entire sum equals g of x, which is good because we're solving this differential equation here where the right-hand side is g of x. This is the general procedure that we'll be following. So if we look at our procedure, step 1 we should hopefully be feeling comfortable with because we've explored solving these homogeneous differential equations. It's more so the second step of finding the particular solution that's going to be part of the learning curve, something new to look at. As has been the theme with differential equations, doing this will involve quite a bit of guessing, making educated guesses as to what the particular solution will be. But that's what this video is for, to walk us through some of those. So let's try to solve a couple of problems. Okay, so here we see a second order differential equation that is non-homogeneous. The right-hand side is not equal to 0. So we'll start by going through our procedure. First, we'll try to find the complementary solution. So to do so, we have to consider the homogeneous version of this differential equation, which would be y double prime minus 2y prime minus 8y equals 0. We see that this is a constant coefficient differential equation, so we'll solve it as follows. And again, if you haven't watched that video, I highly encourage watching it because I'm going to speed through this. The way we do this is we guess y equals e to the kt, y prime equals k e to the kt then, and y double prime is equal to k squared e to the kt. We can substitute back in. Now we can factor out an e to the kt. Now we look at our auxiliary polynomial, and we can factor it as follows. K minus 4, k plus 2, which tells us that k equals 4 or negative 2. Since we guessed y equals e to the kt, we use both of these solutions, plug them back in, and take a linear combination. So that means the solution is y, we'll put the subscript c, since this is our complementary solution, and this will be y sub c of t will be c1 e to the 4t plus c2 e to the negative 2t. So this is our complementary solution. That is step 1 complete. We've found the homogeneous differential equation and we've solved it. So now comes the question, what is our particular solution? What is going to be one function that when we plug it into here, we will get the right-hand side? And again, we have to be guessing, and we'll be smart with our guess. So way back when we were discussing these constant coefficient differential equations, we guessed y equals e to the kt because the derivatives preserve the exponential, and then we would have like terms, and that would be equal to 0. Well, if we use that fact of preserving the exponential, the right-hand side is exponential. So perhaps this function of y must also be exponential. We'll take the derivatives, somehow combine these like terms, and hope that it equals 5e to the 2t. Except right now we don't have this k to worry about. We know that we want k to be 2t because there's a 2t on the right-hand side. So in fact what we'll guess is e to the 2t, but we should be aware that any sort of constant multiple of this is not going to affect it. So we will find what constant we have to put in front of here. A could be 1, and it would just be e to the 2t. A could be 7. A could be pretty much anything. But we're pretty satisfied with this guess, that when we take the derivatives, y prime and y double prime, the exponential term will preserve, and hopefully they'll group together, and maybe we can find a value of a that solves this. So in doing so, let's take the first derivative and the second derivative and substitute in. So y prime of sub p of t is going to be equal to the derivative of this, which is 2a e to the 2t, and y double prime will be equal to 4a e to the 2t. So when we substitute back in for the differential equation, y double prime is going to be 4a e to the 2t minus 2y prime, which is going to be 2a e to the 2t, minus 8y, which we said is just a e to the 2t. And we want this to equal 5e to the 2t. So let's distribute 4e to the 2t minus 2 times 2, 4e to the 2t minus 8e to the 2t is going to equal 5e to the 2t. And sure enough, we have our like terms. The e to the 2t was preserved with our guess and taking the derivatives, and we just have constants in front of them. This cancels with this. So we have negative 8a e to the 2t equals 5e to the 2t. Remember, we didn't know what a was going to be. We figured it could be any sort of value, but we didn't know for sure. We're kind of trying to figure out what that is. We more so cared about the function of t part, and we seem to have guessed that correctly. So let's find the value of a. These two cancel out. You can divide by negative 8 and get a equals negative 5/8. So this all seems to suggest that yp is going to equal negative 5/8 e to the 2t. Well, let's check, see if it's correct. We'll let y equal negative 5/8 e to the 2t. The first derivative, multiply this by 2, will be negative 5/4 e to the 2t. And then the second derivative will be negative 5/2 e to the 2t. When we substitute back in for our differential equation, y double prime is negative 5/2 e to the 2t minus 2y prime, which would be negative 5/4 e to the 2t, and then minus 8 y's, which is negative 5/8 e to the 2t. We can multiply. This is negative 5/2. So that's what happens when you multiply through. This cancels with this, and we're just left with 5e to the 2t, which is indeed the right-hand side of our differential equation. So that means negative 5/8 e to the 2t is a single solution to our differential equation. We turn to step 3 now, because we've found our complementary solution and our particular solution. Step 3 says the solution to our differential equation is going to be y sub c plus y sub p. Y sub c is right here. c1 e to the 4t plus c2 e to the negative 2t. And we tack on y sub p, which is negative 5/8 e to the negative 2t up there. And there we go. That's our answer. And so you can see that we do indeed have a class of functions that satisfies this differential equation. And that class is defined by this linear combination of these terms. The thing is, this linear combination will always make the differential equation equal to 0. So we need an additional term to satisfy the right-hand side. But we still have a class of functions. This is it. This is how we're going to be solving these differential equations. Complementary solution, particular solution, add. Simple as that. Let's do another example. Okay, so here we see another example. Y double prime minus 2y prime minus 8y equals cosine of 3t. So you'll notice that the left-hand side has not changed at all since the previous example, and that's purposeful. But the right-hand side has changed substantially. So let's go about solving this. It's a non-homogeneous differential equation. Step 1 says to solve the homogeneous differential equation. So if we replace this with the 0, we have y double prime minus 2y prime minus 8y equals 0. But we just solved that in the last example, and this is the complementary solution right there. So that's the purpose. I didn't want to spend more time doing things we already know. So now it's about figuring out what's our particular solution. What will y sub p be? So last time we looked over here, saw an exponential, and said, oh, okay, well, maybe we'll just guess an exponential because exponential is preserved when we take the derivatives. Here we see a trig function. And trig functions are kind of okay with derivatives in that they're almost preserved. It's a cyclic nature within our derivatives. Sine goes to cosine, goes back to sine, goes to cosine again, back and forth, back and forth. So maybe that's a good sign. Let's try it. Why don't we? Let's guess a cosine of 3t. Again, we know there's going to be some sort of coefficient, probably. It could be 1, it could not be. The reason why we don't remove the a altogether is because now we're fixing ourselves to thinking that the particular solution must be cosine of 3t, whereas in reality, we can say, maybe it's some sort of multiple of cosine of 3t. We'll figure out what that multiple is later. So again, we're guessing sort of like a class of functions and choosing the correct one. So this seems like a pretty good guess. You know, this will hopefully get preserved along the line, and we'll see what happens. So we'll take the first derivative. Derivative of cosine is negative sine, but you do the chain rule. So it's negative 3a sine of 3t. And then for the second derivative, sine goes to cosine, chain rule, negative 9a cosine of 3t. And so let's substitute back in. Y double prime is negative 9a cosine of 3t. So we've substituted. Now we'll distribute. Now we can group like terms, namely the first and the third term. And now ideally, we'd like to solve for a. So if we look on the left-hand side, we want it to be equal to the right-hand side. On the right-hand side, we see a cosine of 3t, and that's found here. So for those to match, we would want negative 17a, this coefficient, to equal 1, because then we would have the same cosine 3t term on both sides. But here we have this mysterious sine term, of which there are none on the right-hand side. So this would be saying 6a should equal 0. There's no solution for a, because here it would mean that a equals 0, and here we would need a equal to negative 1 over 17. We can't have both of these. So it seems like our guess was wrong. And perhaps we should have thought about that. Like, the derivative is cyclic with cosine, but we would be putting a cosine term here, a sine term here, and then a cosine term here. There would be nothing to cancel with this sine term. Like, it's just there alone, and that's the problem we faced right here. Okay, so if we're looking for something to cancel with the sine, why don't we guess a sine term for y? Because then when we take the derivative, this will be cosine, but this will be sine, and then this guy and this guy can cancel, and we'll be left with just a cosine, which is the right-hand side. Maybe that's a better idea. Let's try it. So now let's guess y equals a sine of 3t. Let's take the first derivative and the second derivative. And now let's plug it back in. We've substituted in our y, y prime, and y double prime. Let's distribute. And now let's combine like terms. And maybe at this point you're shaking your head in anguish and already seeing the problem. If we do a similar argument to what we did up there, by looking at what a should be, again, we can look for the cosines, and this would tell us that negative 6a should equal 1, but again, we have this sine term here, and this would say negative 17a should equal 0, and again, there's no solution. What went wrong? What's wrong with this? I thought the sine terms were going to cancel and we would be in good shape. The issue is that even though we had freedom with A, we didn't have so much freedom with the function associated with A. We were fixed to sine of 3t. And even though when we take the derivative, this sine term is cyclic, it goes sine, cosine, sine, whatever's in here, this 3t, affects our coefficient. It goes to 3 to 9. The coefficients of our differential equation are fixed. We don't have the freedom to cancel these out because there's too much relying on other factors that we've already been associated with. This sine of 3t term, that messed things up. So what? What do we do? Cosine doesn't work, sine doesn't work. Why not both? Okay, so cosine and sine didn't work individually. Let's use them both and take a sum of them. It'll still have the characteristic that the derivatives are cyclic. There's just a lot more terms to consider, and if we're just adding them, that shouldn't affect the derivative too much. So we'll guess a cosine of 3t. And again, we're sticking with this cosine of 3t because we see that here. It wouldn't make sense to guess 5t because when we do derivatives and stuff on this side, where's the 3t going to appear? So we'll stick with the 3t here. But now we'll add to that in our guess b sine of 3t. This is going to be our guess. Let's take the first and second derivative. So we have our first and second derivatives. Now we're going to substitute and ideally solve for a and b. There's two variables now, which is a little bit annoying, but maybe that's okay, because we've seen before that we have two equations where we had like negative 6a equals 1 and negative 17a equals 0. There were two equations. If we have two variables, there's a more likely chance we'll be able to solve for both of them. So let's substitute back in. I'm running out of space over there, but I kind of squeezed it in. And all of that is going to equal cosine of 3t. I kind of left that off, but I'll try to add that back in. So now we can distribute and hopefully combine like terms. In fact, I'll just do that all in one go. Okay, so we've distributed and we've sort of grouped like terms, but we've factored it out. So we've looked at the cosine 3t terms, which are here, here, and here, factored that out, and took the sum of their coefficients. And then for sine of 3t, did the same thing, and then sort of just combined within these brackets. So again, this sum should equal cosine of 3t, where whatever's in our brackets are coefficients, because a and b are just some sort of constant value that we're trying to solve for. But now things look a little bit nicer, because we want the coefficient of this to be equal to 1, since there's 1 cosine 3t on the right-hand side. So that tells us negative 17a minus 6b equals 1. For the sine 3t term, there's 0 sines on the right-hand side. So that tells us that 6a minus 17b equals 0. There we go. We have our two equations, but this time we have two unknowns. So now we can find values of a and b. And this comes back to the reason why we guess sine and cosine sum together, because we utilize the cyclic nature of them, but we weren't able to cancel them out. So we just added them both in, and then now the coefficients will handle everything and cancel each other out. So we can solve the system of equations. I don't want to spend time doing that because it's like 10:30 p.m. and this takes too much time. So I'll sort of just give it here. So I believe that the solutions to this system of equations is a equals negative 17 over 325 and b equals negative 6 over 325. And if we use these values of a and b in tandem with our particular solution, we can construct yp to be equal to negative 17 over 325 cosine of 3t minus 6 over 325 sine of 3t. And again, you can verify that this is a particular solution by taking the two derivatives of this, substituting it back in, and seeing that we'll get a cosine of 3t on the right-hand side. And now we do our final step, where we find our solution y by taking the sum of the complementary and particular solution. So our final solution will be y equals yc plus yp, which is c1 e to the 4t plus c2 e to the negative 2t minus 17 over 325 cosine of 3t minus 6 over 325 sine of 3t. There you go. Another solution. Quite exciting stuff, isn't it? Let's do, I think there's like 3 more, so let's get through those. Okay, so here we see example number 3, and I assure you this one will take a lot less time. We have y double prime minus 2y prime minus 8y, the very common left-hand side we've been seeing, equals 5e to the 2t plus cosine of 3t. Well, that seems hard. What are we supposed to guess? I mean, I presume we could guess some sort of form of an exponential and a trigonometric function. That seems like a lot of work. But wait a second. If I covered up this cosine of 3t, and that was just our right-hand side, 5e to the 2t, we've already solved that differential equation. Similarly, if I covered this up and just cosine of 3t was on the right-hand side, we've also solved that differential equation, right up there. If only there is an easy way to combine our two solutions. And I'll write down the solution of this differential equation. So when this was our differential equation, our solution was... This was our solution when this was the differential equation. When that was our differential equation, the solution was right here. If only we could combine these in such a way. And here we have a theorem. If yp1 of t is a particular solution to a differential equation of this form, y double prime plus p of t y prime plus q of t y equals g1 of t, and yp2 is a particular solution to this differential equation, where the left-hand side is identical to the other left-hand side, but the right-hand side is different, then when we take a look at the differential equation where the left-hand side is still the same, but the right-hand side is the sum of the two right-hand sides, then the particular solution is the sum of our particular solutions. So when we turn back here, we can find a particular solution to this differential equation by taking the sum of the particular solutions to this differential equation and sum that with the particular solution to this differential equation by this theorem here. So that would tell us that y sub p will be equal to our particular solution for this differential equation was negative 5e to the 2t, negative 5/8 e to the 2t. And the particular solution from this differential equation is from here on. And again, we're taking the sum of them. This would be a particular solution for this differential equation. Finally, we can find the entire solution to this differential equation by taking the sum of the complementary solution and the particular solution. I'll just write it down here. There you go, summed all together, that's our solution. So a quick example this time, but this theorem is super, super helpful to know and can save you a ton of time. Surely guessing like yp equals ae to the 2t plus b cosine of 3t plus c sine of 3t. I'm almost convinced that this would work as a guess for yp, but then you take the first and second derivatives, there's 3 variables, probably 3 equations with 3 unknowns. That seems like chaos to solve. This was just so much easier. So remember this theorem. Let's do another example. Same left-hand side, right-hand side is now t cubed, a polynomial term. Complementary solution we already have. Let's make a guess as to what our particular solution will be. Well, we've seen that our particular solution is somehow related to the right-hand side. We've seen an exponential term and we guessed an exponential term. We've seen a trig term, we've guessed a trig term. It only makes sense to guess a polynomial term here. I mean, let's just see if we guess a t cubed. Like, what else do we have to reason with? I mean, things probably won't be preserved because when you take the derivatives of polynomial terms, not much is preserved. But let's just see what happens and go from here. First derivative, second derivative. Substitute. And there we go, we kind of see our issue. We have a t cubed on the right side, so looking here, that would tell us we want negative 8a to equal 1. But this t squared term tells us that negative 6a should equal 0, and here, this 6a should also equal 0. These second 2 equations can be satisfied with a equals 0, but here we would need a equal to 1/8, negative 1/8. So that guess isn't going to work. And we'll employ a similar strategy to what we did for trig functions, where we'll guess similar terms, sum to our original guess, to cancel out the unwanted terms. So here, it's all of the lower powers of t that we want to cancel out with it. So we're going to guess accordingly. So let's amend our guess. We'll keep the a t cubed term here, but now we'll add on every power of t lower than it, and hopefully that'll cancel things. So we'll throw in a bt squared here, a ct, and then a constant term, t to the 0. And let's just see what happens when we plug this in. It's a lot of variables, but maybe something good will happen. First derivative, second derivative, and now we substitute. That's a lot to work with, but let's see what happens when we multiply and do stuff like that. And now we'll combine and factor by like terms of powers of t. So like first is the t cubed term, and that's only being multiplied by negative 8a. And then we look at the t squared terms. There's one here, so this is a negative 6a. One there. That's it. The t terms, 6a minus 4b minus 8c, and then the constant terms. It's a whole lot of algebra, but this gives us a bunch of equations. There's only a t cubed on the right-hand side, so only this must be 1. All of these other parentheses must be equal to 0. So we can write that here. Negative 8a equals 1. And that just tells us that a is going to be equal to negative 1/8, so we've handled that. The second one tells us negative 6a minus 8b equals 0. But we can substitute in our a equals negative 1/8, into there, and we get 3/4 minus 8b equals 0. And then solving for b, let's see, we get b equals 3/32. Then we turn to the third equation. 6a minus 4b minus 8c equals 0. We know what a and b are, so we can solve for c. So 6 times negative 1/8 is negative 3/4. Negative 4 times 3/32 is going to be negative 3/8. And then that's all going to equal 8c. So we've just added 8c here. Let's see, this is negative 6/8. So this is negative 9/8 overall. And then we can divide by 8, and c equals negative 9/64. And then the last term. Okay, substituting in, 2 times 3/32 is going to be 3/16. Minus 2 times that will be plus 9/32. And that's all going to equal 8d. This is 6/32. 6 plus 9 is 15/32. But then we divide by 8, and that's 256. So we have values for all of our coefficients. And returning to our guess, this would suggest that our particular solution is going to be equal to negative 1/8 So that's our particular solution. And to close out the problem, we just add the complementary solution to this. So we'll just say that y is equal to this plus our complementary solution. And boom, another question, this time with polynomial on the right-hand side. All right, I probably should be going home pretty soon because it's very late at night now. But I feel like this example is super important, so this is the one we're going to end on. It's also the last example I prepared, so that worked out coincidentally. Here we go, same left-hand side, new right-hand side. This time it's te to the 2t, a polynomial term multiplied with an exponential term. Let's say I covered this up and it was just equals t. Well, we know how to solve that. That's just a polynomial term, so we would guess something like at plus b and then solve like normally. What if I covered that up and it was just equal to e to the 2t? Well, that would just be an exponential term on the right-hand side. We would guess a e to the 2t and solve for a there. If only there was a theorem that involved taking the product of these two solutions. You know, we had one for adding the two. What if there was one for multiplying them? Got him. Okay, there's no theorem. Unfortunately, we don't have that nice theorem that we can work with. But what we can do is multiply our guesses and then solve from there. So we'll pretend as if we only saw a t here. Then we would guess yp equals at plus b. Remember, for polynomial, we had the normal polynomial term, and then we added all powers less than it. And if we just saw an e to the 2t, we would guess some sort of c e to the 2t. That would be our guesses individually. When we see a product like this, why don't we just guess the product of our two individual guesses and work from there? So distributing this out, we would be guessing, this becomes ac te to the 2t But remember, this is just supposed to be a constant which we'll eventually solve for. So I don't really care it being AC. I can just give it a single variable name. And then here we have plus BC e to the 2t. And again, I don't really care about the product. I just want it to be a constant, so I'll call it B e to the 2t. So let's work with this guess and hope that we get things right. Let's take the first derivative. To take the first derivative, we have to take the derivative of this, which involves the product rule. So I encourage you to do it on your own. I'll sort of write it out, and hopefully we match. So this should be the first derivative, and you could like factor out a common term there, but I don't really want to do that since I'm taking the second derivative. So let's do the second derivative. Again, you'll have to use the product rule. So hopefully after taking the first and second derivatives, you got these two respectively. I've checked my work, so I'm pretty sure I'm correct, but knowing me, I probably made a mistake here or there. So now we can go back into substituting and hopefully find values of A and B. Man, that's going to be a lot to write. Let me use another board. So we substitute. So this is our massive equation. We can distribute and combine like terms. This cancels with that. And then let's see. So we have a single t e to the 2t term here. So that's negative 8a t e to the 2t. And then for the e to the 2t terms, this is 4a minus 2a. So that's 2a total e to the 2t's. And then we have 4b e to the 2t minus 4b, so those cancel. So then it's a minus 8b e to the 2t. And they'll sort of just factor this out. And once again, we have two equations. We see a 2e to the 2t term here. Its coefficient is 1, which means this negative 8a term must be equal to 1. We see an e to the 2t term here, of which there are none on the right-hand side with a constant coefficient. So we need this to be equal to 0. So we have negative 8a equals 1, and 2a minus 8b equals 0. The first one tells us that a equals negative 1/8. And we substitute that into here. We get negative 1/4 minus 8b equals 0. So that means b equals negative 1/32. And so now we can use that to construct our particular solution. We guessed that we were looking for A and B. So this tells us that our particular solution, substituting A, is negative 1/8 t e to the 2t minus 1/32 e to the 2t. And again, to get our final solution, we combine the complementary solution with the particular solution to get our final answer. And there we go. Another example, this time with a more complex right-hand side. Keep this strategy in mind. If the right-hand side looks too complicated, try to break it down into individual things that are more manageable, and then take the product of what you would guess as your normal guess for the problem, and then work from there. Let's conclude the video. Alright, so in conclusion, these were the 3 steps we followed. When faced with this kind of differential equation, we solve the homogeneous differential equation to get a complementary solution, y sub c. Then we find a single particular solution, y sub p, which we do so by guessing, and then we combine our two to get our final solution, y. As a general guide of what to guess, if g of t, which is the right-hand side of your differential equation, is some sort of exponential, k e to the bt, for real numbers k and b, then a good guess to make would be a e to the bt, and then solve for a. If the right-hand side is some sort of trigonometric function, whether that be just a cosine or just a sine or the sum of them both, so a, b, and k are real numbers, then we'll guess a cosine of kt plus b sine of kt. So this was the first example we did together. This was the second example we did together. If g of t is an nth degree polynomial, then we'll guess a sub n, which is a constant which we'll solve for, t to the n, so maintain that degree n, but then add to that every degree below it. And this was the fourth example we saw, where the right-hand side was t cubed. Don't forget the theorem about the sum of particular solutions, and don't forget the strategy about multiplying particular solutions, or multiplying your guesses to particular solutions to formulate a new guess. This should equip you with a certain class of these non-homogeneous differential equations, particularly those focused on constant coefficient non-homogeneous differential equations. And this is mostly because step 1 involves us to solve the homogeneous differential equation, and we're mostly accustomed to solving those kind of differential equations that are homogeneous, but there's also some other reasons why this method is best for constant coefficient differential equations. Remember, this is called the method of undetermined coefficients, and that name comes about because we're making these guesses with coefficients that are undetermined, but then we go and determine them. It's a long video, but there's a lot of information in here. I hope it helped you, and I hope you learned a lot. In the next video, we'll explore another, even more powerful technique to solve these kinds of differential equations. So get excited for that. As always, take care and see you next time.